Good evening. It gives me great pleasure to introduce Professor Jeffrey Froyd, who is recognized worldwide as an engineering education pioneer for his achievements in various areas, including integrated curriculum development, evaluation, adaptation, institutionalization and propagation of educational innovations, curriculum redesign, and faculty development. He has served as project director for National Science Foundation, Engineering Education Coalition, in which 6 institutions systematically renewed, assessed, and institutionalized innovative integrated undergraduate engineering curricula. He has offered many faculty development workshops all over the world on curricular change process, curriculum redesign and assessment in US and abroad. In particular, he has been associated with Teaching Learning Center. He has been mentor of Teaching Learning Center of IIT Madras. He started the association with IIT Madras started in 2009 when they invited him to hold a faculty development program. And since then, he has been visiting IIT Madras every year, holding workshops, mentoring faculty, and mentoring the center. So at present, he is a faculty member in Department of Education Engineering at Ohio State University. He has vast experience in the area of education, and he is on associate editor of many journals, but in particular, he is editor-in-chief of IEEE Transactions on Education. So he has come all the way, despite his health and his time constraints, to be with us. He's going to hold a 2-day workshop tomorrow and day after tomorrow for IIT faculty on research-based teaching practices. So this is a lecture on overview of what is going to come, and in fact something even more than that. So with this brief introduction, I would like to invite Professor Froyd to present a lecture.
Thank you very much for the honor of being invited to talk to all of you, and thank you for taking time from your schedules to come, and I hope the investment of your time is worthwhile. We're going to talk today about research-based instructional approaches. Now, it would be great for those people in engineering and math and science disciplines who are used to precision in terminology if there was widespread consensus on what research-based instructional approaches meant. Unfortunately, that's not the case. So to help you to understand that that's not the case, I compiled a brief list of research-based instructional strategies. Yeah, and that's a brief list. Okay, it is not a complete list. It is not a list that you are expected to read, but it is a list to give you an idea that there are a very large number of research-based instructional strategies that people mean when they talk about it, and they aren't very consistent in their use of the terminology. And so you'll find a number of instructional strategies that we talk about today will have various names, and that is just a function of the situation. What I want to concentrate on, though, is the evidence supporting the efficacy of these strategies. Because while people may be familiar with one or more of those strategies, I find that a vast number of people are not familiar with the evidence supporting that. To compile the evidence, I'm going to take a historical point of view for a couple of reasons. One, I think the historical point of view gives you some organizational scheme. And second of all, by starting with the earlier studies, you'll find that they form a basis for some of the later studies. So we're going to begin with a fairly well-known study. People in physics will know this study. It was a study of 6,000 students that took an introductory course in physics mechanics. An introductory course in physics mechanics is a fairly common thing to take, and so they were very interested in the learning that goes along with that. Now, prior to that, to enable that, 2 things had to come about. There had to be 2 pieces of machinery. The first piece of machinery is shown on the left-hand side in the acronym FCI. For those people not familiar with the acronym, that means Force Concept Inventory. It was a multiple choice test compiled in about 1990 by two researchers at Arizona State, and it was accepted roughly at that time period by the physics community, saying students who complete an introductory course in mechanics should be able to answer these 33 questions correctly. It wasn't, the questions are not computational, the questions are qualitative reasoning type of questions. They're all, here's a situation, what do you think happens A, B, C, or D, or E? Okay? They weren't intended to be trick questions. They were intended to be questions that said, basically, if you know the concepts that we teach in introductory mechanics, then you'll get these questions right. And the physics community said, yeah, our students should be able to do these questions at the end of the thing. However, they began to give the test to people, both before the physics course and after the physics course. And Hake compiled a bunch of scores from across 6,000 students, some of which were taught using interactive engagement, which is shown in the hollow point thing on the left, things that are hollowed. Some were taught using traditional lecture. Those are shown with the colored things in the yellow. Now, the horizontal scale is the score that they got on the force concept inventory before they took the course. So the best that they could do was 100%, and the worst that they could do was 0. You'll find that nobody got 0 on a class average, and the class average didn't come anywhere close to 100. In other words, when they started the course, they had misconceptions or alternate conceptions about physics. And the vertical axis is the gain. Now, Hake introduced this idea of gain by saying, okay, if you take the test before, and then that means that you got a certain number of the questions wrong if you didn't get 100. So we'll use that difference as the denominator. In other words, the denominator is the number of questions that you got wrong on the pre-test. So hopefully on the post-test, you don't get those questions that you got right wrong. So the denominator gives you a sense about how many additional questions you're going to get right. And that's the numerator, is the additional questions that you got right. There are various writings about this, but the gain, and if you notice the gain on any of the charts on the left, nobody at the end of the thing gets 100%. In other words, even after the course, they didn't get it all right. In fact, you'll notice that for this things taught with traditional, that is the colored yellow dots, that they barely got a 20% gain. You look at the average down there, it's about 23%. In other words, that they only got, of the questions that they got wrong on initially, they only got 23% of those right at the end. All of those taught with interactive engagement did better consistently. They got about half of those questions right. They still didn't get them all right. And so the interactive engagement showed a gain roughly of, they did twice as well as the students taught with traditional lecture on the force concept inventory measured pre to post. Yes, sir? Yes. The same questions were asked again. Whether they remembered the questions is an entirely different issue. So some people have asked for an A-B version of the force concept inventory on the idea that they might remember. But if you look at the performance, we're not worried currently about whether they remembered the right answers or not. Now, the graph that you see on the right, the two graphs are rarely displayed together. But the graph that you see on the right is the same kind of thing done with the signals and systems concept inventory. So, very different subject. This is a basic course in electrical engineering. And they developed a set of questions for the signals and systems course. You can see we have the same pretest. Not a lot of people get the pretest right. And you can see that we get a gain. And we get 20% roughly with the traditional lecture, about 40%, a little less this time with interactive engagement. In other words, on a very different subject, on a very different year, because typically students would take this in their sophomore or junior year, then they take the traditional mechanics course. Very different teachers. We're now teaching electrical engineering faculty members. You see the difference between traditional and interactive lecture as about twice this much. And for the signals and systems concept inventory, it's the same questions on the second round away. Now, This is the same graph this is the same data as the one displayed on the left-hand side in the earlier figure. We're just positioning the data differently. This time the gain is on the horizontal axis, so we prefer to be right about here, 100% gain, but we're not anywhere close. But most faculty say, well, it's sort of instructor dependent. There would be some really good interactive engagement instructors, and there would be some really good lecturers. Okay? The red is shown in lecture. Okay? And so here, 50% of the courses that were taught in lecture get about 24% gain. About the average that we saw, that's kind of median. Okay? And the ones taught in green are the fractions taught with interactive engagement. This means that the worst people at interactive engagement are as good as the best people at lecture. In other words, it would submit to you that it isn't instructor dependent, that people who use interactive engagement generally do a whole lot better than lecture, no matter who the faculty member is. Next, I want to look at a course entirely different. This is a chemistry course taught at the University of Wisconsin. It was taught, in this case, the study was done with 2 faculty members. Both faculty members were voted as outstanding teachers. One used reflective lecturing. One used structured active learning, in which the students were much more involved. They were actually good friends. They would talk regularly about teaching the course and so forth. And the course was assessed in a very unusual way. Chemistry 110 is the prerequisite for a number of other courses at University of Wisconsin-Madison. They recruited faculty from those subsequent courses, and they said, okay, look at the subject that you teach and what you want your students to know about what they should get out of Chemistry 110, and ask them questions in an interview. So one by one, they had the students come in, and they had a segment of faculty members interview the students with a set of standard questions. Then the faculty members would note the answers to the interview questions, and they would record their estimates of how well the students were doing on several different scales. The private foundation that sponsored this was very glad for the detail and the care with which the assessment was constructed. They were slightly less enthusiastic about the cost that was invested in the assessment, because it was very thorough. But the assessment showed that both courses were well taught, but the faculty members who interviewed the students could see a distinct difference in the students taught with structured active learning as opposed to reflective lecture. Particularly, they saw a difference in meta-awareness, that is, how the students thought about how they would solve these kind of novel problems that the faculty gave to them. That was the case where the biggest difference, the scale on meta-awareness. Scales on agility and analysis subgroups were less distinct. There was a 25% difference instead of a 50% difference between the two groups. But you could tell a difference. And the faculty all said, yes, the students that came out of the structured active learning displayed more of the kinds of thinking that we would prefer that our students display. So that was another piece of evidence that said that structured active learning was more effective at promoting student learning. However, in a flip side to the story, the faculty member that taught with reflective lecturing saw the data, saw that the students coming through structured active learning taught by his good friend was better. Did the person who did reflective lecturing change the way he taught Chemistry 110? No. So, another set of things. These are meta-analysis. In other words, the meta-analysis, they go through the literature and they identify studies that look like they're going to be about the subject that they're interested in. Then they call those studies and they look at the characteristics of the studies. If the characteristics of the studies meet their requirements, they're included in the group. If they don't meet the requirements, so that they have, in other words, the requirements for certain data and so forth, they throw them out. And so then they collect a bunch of studies together and they have an analysis of them. Okay? And so they look at particularly what's called effect size. Now, if you're not familiar with effect size can be one of three things. It basically is the difference of the means of the two groups over some choice of standard deviation. Now, the three groups differ, the three formulas differ in how they picture the standard deviation. If the standard deviation for the two groups was the same, all of the formulas collapse down to the same one. In other words, I'm taking the difference in the means over the standard deviation. The difference in the formulas depends on how I'm going to compute what I'm going to do for the standard deviation where the two groups are different. So the effect size is basically how much did the mean change would reflect to some estimate of the standard deviation. And you see that for academic achievement, I've got an effect size of 0.64. I've got for quality of interpersonal interactions in the first study that looked at all subjects taught at university level. I've got an effect size there. Change in self-esteem was lower. Change in perceptions of social support with collaborative learning compared to individualistic learning. So, in other words, if you think of a standard deviation in a course that gives you roughly a grade size, think of a 100-point scale. You know, A goes from 90 to 100, B goes from 80 to 90. So your standard deviation in that case is around 10. So that's what you're using to picture your thing. In which case, these are all in the blue of about half a standard deviation. So that's about half a letter grade. The students in the collaborative learning environments did half a letter grade better than the students in the standard lecture environment. That study was repeated. These same people did another meta-analysis. They collected a slightly different set of studies using slightly different criteria, and you'll see that the effect size changes here. This was for all courses, all at the university level. Then, slightly later, 1999 was when this paper was published. These people, Springer, Stan, and Donovan, only looked at courses in science, technology, engineering, and mathematics, referred to in the United States as STEM courses. And so they looked at it for academic achievement, attitudes, and retention. And again, you see a half of standard deviation difference. So that was 3 studies, all published within basically a year of each other. And they were all collected in a study in a paper that was done by Michael Prince. It's been cited over 4,000 times saying, yes, active learning does show a significant improvement over traditional lecture. Peer instruction. Peer instruction is always equated with a guy named Eric Mazur. He's a physicist, taught at Harvard. He got started in this business because he looked at the force concept inventory results saying students who take a physics course don't do much better on the force concept inventory at the end of the course than they do at the beginning of the course. Eric Mazur teaches at Harvard. Eric Mazur is a Harvard professor, and he says, that will not happen in my class. I teach well. So he gave the test to the students. He gave the force concept inventory to the students at the beginning of the course. He gave the force concept inventory to the students at the end of the course. The student at the end of the course had an interesting question during the exam for Dr. Mazur. The student said, Dr. Mazur, do you want me to answer these questions on the force concept inventory the way you taught us, or the way I really believe that it works? Raise your hand and says, how should I answer these questions? According to what you taught me or how I usually think about these things? Still, at the end of the course. And Dr. Mazur found out that his students at Harvard did 20% better using his traditional lecture than other people. Now, the entry score, the pretest score at Harvard was higher than other places, but they still only got about a 20% gain. That inspired Dr. Mazur to put in a situation that he refers to as peer instruction. I'll get to that in just a minute. There's a book that he wrote called Peer Instruction. If you're interested in how peer instruction works, that would be part of the lecture tomorrow in the workshop. But he put this in place. Yes, sir. Excuse me? Oh, what? It was reserved on, I don't know. I actually took this. This is from a story of narrative, and at first he will say, I didn't realize that said there was trouble. I don't think he could process the question. Also, I don't think he could answer the question to the student during the test. But that question was a clue to him that something's not right. And so he invented a thing called peer instruction, and they actually tabulated things. So there's two versions of physics. There's a calculus-based version of physics and an algebra-based version of physics. The one in the white is taught using traditional lecture. It's probably the last time Eric Mazur taught using traditional lecture. And the next year he started peer instruction. And the ones in the shaded area are done with peer instruction. And the dotted lines are, this is the game that we saw on the Hake paper. That's why we introduced it earlier, for what's taught using traditional lecture. And sure enough, the class taught using traditional lecture gets about the average. The things taught with peer instruction get either the average for the interactive engagement or better. But in any case, you get, for peer instruction, you get about twice the gain of traditional lecture. The gain is not quite as big in the algebra-based. So there was a whole coalition of schools funded by the National Science Foundation, and they conducted a study of collaborative learning versus lecture. In this study, they asked a number of students, several hundred students were involved in the study, about several things. So they asked, what is your picture of knowledge and understanding of the process of design? What is your ability to do design? You can read the questions there. They asked them, what is your impression about how much you gained in this course? Okay? If the course was taught with collaborative learning in the Excel Coalition versions, you'll see the numbers in the column in the middle. If the course was taught using traditional lecture, you'll see the numbers taught on the right-hand side. In every case, the numbers in the middle are significantly larger than the numbers on the right-hand side. The ends vary depending on which course we were talking about, which questions were asked. But in any case, we're talking about a reasonable number of students so that you could see the difference is going to be for a reasonable number of students and is statistically significant. So even though these are students' self-reported gains, with the number of students, it's again saying that your collaborative learning is giving you better results in terms of the student perception of the game than traditional lecture. Now, there is a kind of a history to this. The first things that you looked at in terms of Hake's paper was done with physics. Eric Mazur's work was done with peer instruction in physics. So in an entirely different area, in chemistry, they looked at this peer-led team learning approach, which again is another approach to getting students more actively engaged in their learning than traditional lecture. Here we tabulate things. So the workshop version is what used peer-led team learning, and the control is what used traditional lecture. Okay? The number of students in each group, the total points are the points in that chemistry course. Okay? So I don't know how many they're out of, but the students that in the workshop got an average of 544. Students in the control group got an average of 478. And again, you'll see the famous effect size of about half. This was for the male students. So we broke it out by groups. For the female students, you see a similar difference. In this case, the effect size is larger. If I look at the majority population in the United States, that generally means white. You'll see that the effect size, you'll see again the difference. Again, statistically significant. The effect size is again slightly bigger than a half. And for underrepresented minorities, smaller numbers because they're minorities. And you'll see the effect size is slightly smaller. It's still on the order of a half. We're getting that half letter grade, again, for peer-led team learning, which is another approach to getting students more actively involved. This peer-led team learning was pioneered in chemistry instead of physics. You can see the historical kind of thing in that physics tend to get started in this earlier, and then chemistry rolls along, and we'll see a little later biology rolls along in that area. Another one. So this is active learning versus traditional learning. This was back to physics. This was in 2009. So they looked at students' understanding of force, acceleration, and velocity. This was the solid bar at the bottom of each of the three bars is what the student's average was before instruction. after instruction, that's the middle bar, traditional instruction, well, they all gained. But with our active learning engagement, that's the gain that we got on the upper bar. So you see that in terms of force, as it points out, even after the lecture, even after the course, only 20% of the students have a clear understanding as conveyed by the answer to this question on force. Whereas the students who have been through the more engaging method, you're close to 100%. Process-oriented guided inquiry, almost always referred to its acronym because people get tired of saying process-oriented guided inquiry learning. They refer to them as Povo. And then people involved in the Pogo group are sometimes called Poglers. This was, again, initiated in chemistry. The basic idea of Pogo is a very unusual concept for people to grab a hold of. If you look at a Pogo class, you will see the instructor doing virtually no lecture. They have carefully designed a number of activities. Usually the activities are short, something on the order of 15 to 30 minutes. But the activity has been carefully designed so that when the students go through the activity, it's an activity they are likely to be able to complete, and that they will have an understanding of the subject, the topic, the concept that the activity was meant to address. So faculty will spend literally hours, if not days, devising one of these activities, and then they'll share it among the group. So typically a Povo class comes up with activities that were developed by multiple people because nobody has time to develop all of the individual activities together. And so that they're very carefully structured, the students work on these activities in very small groups, and the faculty work with them to help them, guide them through the process. So the guiding is done in two ways. One, it's done by careful construction of the activities so that they're connected with what the students' entering knowledge is likely to be. And second of all, there will be lecture on how you should think about this subject, how you might work through these kind of exercises. And they will also work, if a team is having a problem, they may go and talk to the team about, what's holding you up, how are you going to work through that, and so forth. So it's all about process and guided inquiry. Pogo is now a very well-established group. They have annual meetings of people in Pogo. They keep track. In general, they will talk about the fact that the percentage of students passing their chemistry course is much higher than the percentage of students passing a traditional lecture course. Well, the concern would be if I tell you that more of his students pass the course than your students, you go, oh, well, he's an easy grader. To look at that, they then develop some consistent exercise things. So this university would give the American Chemical Society organic chemistry test. That university normally scores in the traditional lecture courses in the 64th percentile on the course, on that exam. When they did the Pogo section, the students scored in the 81st percentile, even though they had an attrition rate of 8% as opposed to 26% in the traditional course. So they were passing more students and scoring higher on a standardized exam. So this is just one example. The Pogo site has a number of different studies, had a number of different universities that have used Pogo, and they get similar results. I would say to you that if you're interested in exploring this, Pogo has produced a set of textbooks. There's a Pogo approach to teaching general chemistry. You haul out the general chemistry course, it doesn't tell you a bunch of topics. It says, here's an exercise, set your students down, give them this data set, ask them to come up with an explanation. Wow. Next exercise, here's a data set, here's what, ask the students to come up with how you're going to explain the data set. Wow. So the textbook is just a bunch of exercises to help the students work through concepts. So they've compiled Pogo textbooks for general chemistry, organic chemistry, inorganic chemistry, and I have a colleague that just finished a Povo set on analytical chemistry. There are actually Povo books in other subjects as well. It's branched out beyond chemistry. Well, one of the questions about research-based instructional strategies is how do the students react? They're being asked to do something very different. So, by the end of the Povo course, this is how the students thought about the traditional lecture. Blue is strongly agree, they like it. Agree, neutral about this, disagree, and strongly disagree. Here are the same chart for the students coming through the Povo course. You can see in general the students heavily prefer the Povo approach as the thing. Now, that is not to say that they, if you check with them on the second week of class, that they really think that this is great, because they're going, oh, this is very different. But by the time they hang with it through the whole thing, they are now convinced that this way of approaching really is something they prefer, and the data shows that they actually learn more of the subject. For those people interested in following up, there are a number of references there. You're not expected to copy this down. I'm sure that some provision can be made to make this available to you. But I didn't want you to leave thinking, well, there are no papers on this thing that you could study. Peer-led team workshops. Okay? Why is this called peer-led team workshops instead of peer-led team learning? Okay, who are the people that did peer-led team learning? Chemistry people. Who are the people doing peer-led team workshops? By golly, if we're in biology, we are not going to do the same thing as chemistry. We're doing peer-led workshops. We are not doing peer-led team learning. We're doing peer-led workshops. Now, I would challenge you, if you looked at how they implemented peer-led workshops and how they implemented peer-led team learning, I would challenge you to find much of a difference between the two. But by golly, if we're in a different field, we're going to do something different. This is, yet again, one of the problems with people getting into the educational research is that we're not a big fan of consistent use of terminology. And as a matter of fact, if you invent a method and then he invents the same method, he's going to call it something different. And it's his method. But in peer-led workshops, so here's the lecture gives you the grade distribution across the top for the lecture. The workshop, next level down, gives you the grade distribution in a workshop. You see that we're getting more A's, more B's, about the same percentage of C's, about the same percentage of D's, and a lower percentage of F's and withdrawals. So more people are making it through the biology course. Again, there's enough mechanism in place to say that they are in fact learning biology as opposed to easy grading. So the reason this is in 2009, this is because if you look at historically, biology did not get started in using research-based instructional strategies as early as physics or even as early as chemistry. So they came a little later to the party, but they're now reproducing their own set of studies. Now, this study was introduced because there's always concern that, well, some faculty members are just better at this active learning engagement kind of stuff. I'm a really good lecturer. We saw Eric Mazur as a really good lecturer earlier. You did better if you did something different. This was a study that the entire physics department at California Polytechnic State University, if you refer to that, say that too often, you using the acronym Cal Poly is how they almost always talk about themselves. So this was included. I included this because they actually took a study involving all of their instructors, not just instructors who volunteered to do it and some others continued with lecture. They got all of the instructors, I don't know how they got it, but they got all of the instructors in the physics department at Cal Poly to shift over to using a studio physics, more engaging approach. There are the grades. Done by semester, and you'll see they have a different marker for the different instructors. We've got 10 different instructors. The bottom number is the Haig's traditional average. When Cal Poly offered the traditional course, they did slightly better. They got around 30% gain. you'll see the studio average is the solid line, and so much higher. Again, 60% gain versus 30% gain. You'll see twice as good, but you'll see the variation by instructors. Now I'm told, this is not the data on here, I'm told that in the Winter 99, you see that there's a figure up there that's way above 0.70. That is the highest gain recorded in this whole study. It's recorded by a couple of instructors. One of those instructors, actually, when they did the pre-test, he was the lowest scoring one using traditional lecture. Shifted over to using this approach, got the highest score recorded across them. But you see that even though there is distribution, which you would expect, consistently all of the instructors that use this approach were able to raise their scores above the Cal Poly traditional average, and the dotted lines are plus and minus 15% gain around the Cal Poly studio average. So most of the instructors are still within that kind of band. So again, this was introduced to say, no, it's the instructional approach. If the instructor adopts this, and I have a fairly carefully laid out approach for the instructor, I can get the gain no matter what instructor that I'm talking about. Problem-based learning. Problem-based learning was introduced by medical schools in around the 1950s. It was based on the observation that traditional medical instruction has you take about 2 years where you take science courses. Science medicine, you'll take anatomy, you'll take physiology, you may take neurology, you'll take a bunch of courses focused on subjects. And then in your last 2 years of medical school, you will spend in residency applying that material. But most medical schools found that in residency, they weren't happy with the extent to which the students actually applied the knowledge that they were supposed to be picking up in the first two things, even though they did well on the multiple choice test that they were required to take at the end of an anatomy course or a thing. But they really weren't able to apply it in the residency. And so one or small number of medical schools got together and said, well, let's shift and we'll do what is referred to as problem-based learning. That is, the first day that a student arrives at medical school, the first thing they see is they present the student and say, here is a patient. They actually give you a patient, they present it with a piece of paper, and they say, the patient is showing these symptoms. What's your diagnosis of the problem, and what's your prescribed treatment? You need to come back with an answer within a certain number of days, and then they'd send a small group of students off to work with that. Now, problem-based learning has evolved in several different ways since then, and so it's relatively hard to get a handle on the extent to which problem-based learning is making a difference, because there are lots of different implementations of it and so forth. But in general, the theme is the following. If you look at simple knowledge-based tests, that is, if you look at the knowledge multiple choice, check this answer right or wrong, the students in problem-based learning do just about as well, or maybe even a little less well, than the students in traditional lecture. On the other hand, if you look at any of the complex learning outcomes that you're expected to display, the problem-based learning students do better on those complex learning tasks. In every case, there is no variation there. Here's a bunch of things for people that want to follow up on this. I think the bottom one is the most significant study. This was a 10-year study done at the University of Missouri Columbia in their medical school. It was a 10-year study because they have 4 years of data. I don't know who thought to do this. 4 years of data where they would look and administer a survey to students and say, how are the students, they would actually administer the survey to people who were hiring these students. How is this graduate doing on these set of skills? They listed the set of skills: communication with patients, ability to diagnose the problem, and so forth. They had this whole list. And then they shifted. The whole school went completely to problem-based learning. So then they have 6 years of data on how these graduates did on that same scale with problem-based learning. On all of those scales, every one of those scales, the students that went through the problem-based learning curriculum either did better or just as well. There was no scale on which the problem-based learning students did worse. That's, to me, the most consistent, the most compelling study in terms of the efficacy of problem-based learning. This is the most recent paper. This was published in 2014 in the Proceedings of the National Academy. It was a meta-analysis. So we've seen all of these studies compiled since starting in about 1998 or so. And they decided that it was time to do a meta-analysis of all of these studies. So they combed through the literature. By this time, they were looking at courses in science, technology, engineering, and mathematics. So that it was restricted to STEM fields. And they found 225 studies that met their criteria. Well, met their criteria meaning they could do a meta-analysis. So one of the things they looked at was the percentage change in failure rate. You'll see that in a small number of studies, there was a decrease there was an actual negative. We got more failures in a few of the studies. That's the vertical axis. In roughly, I would say, 4 studies of the 225, 4 studies. In general, though, there was decreased failure rate in 221 studies, and it showed that the average decrease in the failure rate was around 10% across all of the fields. And then they looked at the percentage of the students that failed and the density with which that occurred, and you can see with active learning, there's a substantial decrease in the percentage of students failing the course. Now, again, you can reduce the number of failures by just giving all passing grades. However, we want the students to actually have learned material. So they looked at this effect size, using the Hedges version of the effect size, and they looked at where we could get, on the left-hand side, gains in terms of scores on concept inventories. Gains in terms of scores on exam. Do we have exam data? And you'll see that all of this organized by subject, we all get a positive effect size. Now, the size of the effect size changes between subjects. It differs. You'll see the numbers below are the number of studies in those different disciplines. On the right-hand side, they'll break out failure rates by discipline. So we're getting decreases in failure rates consistently, irrespective of discipline. We can break that out whether we're talking about, on this left-hand side, we could be talking about both exams and concept inventories. On this graph, we'll break out the score, whether we're talking about exam scores or scores on concept inventory. You'll see that in most cases, we had 109 studies that gave us exam scores. So we saw about a 30% or 0.3 or 0.35% gain or effect size there. And the effect size was much larger, but it was a much smaller number of concept inventories. Now, they also were interested in how does class size affect. Class size, as the class size goes up, that is, in this case, that's going down on the scale. As the class size goes up, the effect size decreases. So the class size is influencing the scores. Smaller class sizes get a larger effect. Larger class sizes get a smaller effect. But we're still looking at an effect size of around 0.3 for the large class size. And again, the number there is the number of things in the study. Now, at least one of meta-analysis first got started in medicine because they have the most pressing need. If you have a certain disease, and there have been X number of studies on the disease, all of those studies could say various things about the treatment of that disease. A meta-analysis was introduced to try to make sense and bring meaning to all of those studies on treatment of a certain disease. So they would you're interested in a disease X. Okay, let's look at all of the studies where they treated disease X let's look and say, what are all of the qualifying studies? That is, do we have enough information from the study to do our meta-analysis techniques, compute an effect size, and so forth? Studies that don't meet that criteria are excluded. Studies that meet that criteria are there. So the idea of a meta-analysis got started in the area of medicine because people were most interested in what does seem to be the most effective treatment. So one or more of the authors involved in this study had been involved in similar meta-analysis in the area of medicine, and so knew something about the kinds of things that they would see in a medical study. And what they said was that if you had looked at this number of studies in a medical study, and if you had seen the similar kinds of changes that they were seeing where treatment is versus called active learning, and the control group or the placebo is traditional lecture, then if the condition were that there would have been random enrollment in the treatment, which is almost impossible to introduce in an educational study, but if there had been that condition, then they would have stopped the medical trial right then and there and said, we will not proceed forward with the medical trial because it would be unethical. Given the results that we see so far in the trial, it would be unethical to continue to administer the treatment when studies show so far that the treatment is effective. So in terms of active learning, it said we would stop the trial of traditional lecture and we would do active learning because the data, as shown in this study, is sufficiently persuasive that it convinces, as would be the case in the medical trial, that the active learning treatment is superior to the placebo. Now, you may have trouble organizing this. So in 2012, Presidential Office of Science and Technology issued a report calling for 1 million additional STEM graduates in the United States, I think over a 10-year period. And they also looked at all of the different studies that had been done on the efficacy of various approaches besides lecture. And they compiled those. And they said, okay, here's the type of active learning, in this case, small group and peer instruction. Here's all of the studies that show enhanced learning as a result of that. This, by the way, was published prior to the Freeman study. If you want to look at the results of using a testing approach, one thing. If you want to look at the results of minute papers, there. If you want to look at results of clickers, there. Problem-based learning, at least two of those things. I think they actually left out some studies that would have been good. You saw my earlier list on problem-based learning. Case study approach, analytical challenge before group lecture, group test, problem sets in groups, concept mapping, writing with peer review, computer simulation, combination of active learning. You'll see Freeman in 2007. He's the same author of the meta-analysis that we looked at in 2014. So that's the organization. I compiled that onto all one list, one slide, so if you get the PowerPoint slides, you don't have to look at 3 different slides. And I hope that I have not taken too much of your time, and you may have questions. Yes, sir.
It's a very good lecture. Thank you.
Oh.
I have many questions, but because there are too many people, we'll limit to maybe 1 or 2.
We'll try one first, and we'll be back.
Okay, only one maybe. Which one I don't know. Well, I'll ask the. So these are all based on college students. All these studies are based on college students. And I'm assuming that in high school and before that, these methods were not used for teaching any of this. Elementary, high school. No.
No, they are.
Huh?
There are. So when you look at the literature, there are actually more studies of these methods used in pre-college than there are in college. But when I'm talking to university faculty members, I do not quote pre-college studies because faculty members will say, well, that's true for pre-college, it's not true for us. So I have used only data from university undergraduates because that's the group that we're talking about. However, there have been a large number of studies on a large number of research-based instructional strategies in pre-college. In fact, the number of studies and the number of students involved in those studies is larger than the university studies.
So the question is that if they are not exposed to this kind of learning methods, would students, would faculty face some resistance, or students would not want to participate or would find it difficult?
So that's why I presented this slide. Notice how much they like Povo over the traditional approach. Now, if you're going to do this, if you're going to use an approach, an instructional approach that is different than what your students are used to, you are going to force change on students. You are going to force change on people. People don't like forced change imposed on them. Universal rule. They don't. So, you have to be prepared for that kind of resistance, because there will be resistance, but you are able to address it in two ways. I have a set of colleagues that have finished a study of how you address student resistance to active learning techniques. But the quick summary is you have at least two effective tools. One, when you begin the course, you should explain to them that I am going to do something different. And here's why I'm going to be doing it. First of all, I believe in your learning. Second of all, I have a substantial research base that suggests that this approach will help you to learn better than the traditional approach. And so I'm going to adopt this approach because I'm focused on your learning and not necessarily your initial comfort. So learning involves change. And any kind of change on the part of us generally involves some sort of period of ambiguity, which is interpreted as uncomfortable. So you should address the fact that if they're learning more, they may actually feel more ambiguity or feel more uncertainty because they're learning more. But you should expect that. So I would, talk about what I'm going to do at the beginning of class and why I'm going to do it, and maybe remind them of that from time to time. The second thing is that about 4 to 5 weeks in the course, I would tell them up front, but I would do it 4 to 5 weeks in the course. I'll do kind of a mid-course correction. We'll take time and we'll say, what's going well in this approach, and then what would you suggest as improvements? And then to the extent that you can initiate those improvements, then I would. Sometimes you get a student that says, the class is held at 8 a.m., I would prefer that it would be held at 11 a.m. You don't have any control over that. But to the extent that you can make changes suggested by the students, you will experience a tremendous increase in support because you're actually acting on things that they suggest that you can do. And you go, yeah, that's a good idea, let me do that. Those two strategies alone will help significantly mitigate the resistance, and that is supported by the research by my colleagues on student resistance to active learning. So I can point you to the research on student resistance to active learning if you're interested. Thank you. Yes, sir.
Valay, I'm third undergraduate in chemistry. So my question is, there are a lot of books that are properly written for high school studies. There are a lot of good books that are for high schools,
yes,
for science and basically STEM education. What I feel is there is a lack of books that are specifically targeted for undergraduate studies. So what happens is, some researchers write their books, and for a general, public, as the PhDs can read it, the undergraduates can read it, and I feel that many of the books that are referenced to us, for the course, they're not really targeted for us, and we have to pick and read. So what is your opinion on that?
So I think you're saying that you don't like the textbooks you got. So that's your opinion on. So could there be better textbooks? Yes. Do I think a better textbook would make a substantial difference in your learning? The answer is no. So, time and again, the research on learning has shown that learning has much more to do with what the learner actually does than what the learner reads. So you can read outstanding explanations of concepts. Do they help you? Some. If you are asked to reformulate that concept in your own words, that's a far more effective exercise than any clarity in the part of the textbook. Second, there is a substantial literature in terms of desired difficulty. What does that mean? I'll give you an example of example. They were giving a course to students in college, and half of the students got a textbook with a beautiful, clear font. All of the reading was printed in that beautiful, clear, easy-to-read font. The other half of the students got the same textbook, but the font was fuzzy. It was just a little more difficult to read, just a little harder to make sense out. So which group did better? The group with the fuzzier text. They had to work harder because the text was a little unclear. And so the people that had to work just a little harder to make sense out of it actually learned more than the people that had clearly printed text. So over and over again in learning, people mistake, not just students, people mistake familiarity for competence. They read something, and if they read it and it was clearly explained, they go, it's clearly explained, I can follow it. The problem is that you can follow it. But what you're asked to do on a test is actually do your own. So the clarity in terms of explanation, meaning I can follow it, does not lead necessarily to competence. So improving the quality of textbooks by making it clearer may actually hurt you, based on the studies. Now, if you want to see a TED Talk on this, so I would look for a TED Talk on messiness. It's a 20-minute talk. You'll recognize it because it opens with a story about Keith Jarrett and jazz piano. One of the most entertaining and enjoyable talks, but it makes the point that what we think makes us comfortable makes us learn. And actually, some of the converse is true. What makes us uncomfortable, to a certain extent, is what actually helps us to learn. So that's the whole area of desired difficulty that we want to pose for students. Does that help? I see. No, you hadn't asked a question yet. Then we'll hit you. Yes, sir.
So you had a slide about Excel and collaborative learning.
Excel coalition.
Yeah. So there was one of the points was organization of material. How does collaborative learning help you organize better? Like I would expect organization would be misorganized because you do not have a structural follow substances.
Oh, this one?
Yeah. So the organization is doing better in
far better.
Yeah.
So why is that?
Or what is that in some sense? How is
that's because in a lecture, who organizes the material?
The professor.
Yeah, the professor. So who actually should learn to organize the material? The student.
Yeah.
So a clear presentation by the faculty member of the material means the faculty member is now clear about it. Doesn't mean that the student is necessarily clear about it. If the student has to do a little more work to make sense out of the categories and stuff, which would happen when our group is talking about it, going, oh, well, you see it this way. You see it this way. You see, I got to make sense out of all of these different things that I'm seeing. That pushes the student to have a better understanding of how to organize the material. Again, faculty mistake their clear presentation for the fact that all of that is transferred en masse, without error, without confusion, into the mind of the student perfectly. And that doesn't happen.
Yeah. So is there any kind of recommendation on what is the typical class size should be to try these kind of different active learning approaches?
So the question, is there a class size where, let me put it, first of all, is there a class size that's so big that you shouldn't try it?
Yeah, that's right.
The answer is no. Okay? Because even when we're getting above 110 students, we're still getting a better gain. Now, we're not getting as good a gain as if we had a class less than 50, but we are still getting a better gain. So, yes, we should put it in place. For faculty members, the issue of the larger class doesn't have to do with so much class size as class management. Over and over, this took me a long time to figure out, because in faculty development, faculty would say, I need to know how to teach a large class. Over and over again, it took me a while to decode. What the issue is when you have a large class, this was best conveyed to me by a colleague at Texas A&M in a book. It says, when you are teaching the large class, you are not teaching a class, you are the mayor of a small town. Your ability in teaching a large class depends much more on your classroom management skills and your planning skills. That is, if I'm going to teach a class of 500, I better know exactly what's going to happen every minute of my instructional period, because I can't afford to get a class of 500 people off the rail. If I got a class of 20 people and they get off the rail, I can get 20 people back on track. If I get 500 people off the rail, I don't stand a chance of getting those people back on track, because that's a small town remove. So, if you are going to teach a very large class, it takes a lot more work on planning and classroom management skills. How you're going to do, how are you going to distribute exams? If I got a class of 500, I can't hand out the exams individually, because I just chewed up a whole class period handing out exams. I just have, I need a strategy for handing out exams. I need a strategy for handing out papers. If I'm going to collect homework in class, I've got to collect a strategy for collecting papers. So for the large class, I have to do much more planning. I got to do a lot more organization. And some people are naturally gifted in that area. Other people, they don't do that really well. And so they have to work harder. But the issue for large classes comes down to classroom management, not necessarily effectiveness. In fact, I have a faculty member, colleague, who taught at a large university in the United States, and he would do active learning, and he would have the students work in small groups. And people would say, well, how do you get the students back? And he had a method for getting the students to come back to him. And he had a class of 400. He could get their attention back in 11 seconds. And 11 seconds was considered a poor performance on the part of the students for returning attention. But, this is what's going to happen. Yes, sir.
Actually, I had a follow-up. I wanted to ask the same question also, that about the scalability of these methods, basically. And I totally agree with you about the management part. But ultimately, to process the outcome that comes out of active learning. See, lecturing is essentially infinitely scalable, in principle, in theory.
Yeah. Absolutely.
You can just add rows to the classroom and better audio visual system, and you infinitely scale. But when you have active learning, and the two slides that you put up, they were essentially work done by the students that unless you're reading it and processing it in some way, it means nothing. The definition of active learning is not complete. So that's where. So the question is, it's going to need many human processors if the work is going to remain subjective, like the part describe this concept in your own words, or anything that is descriptive. You're really going to need an army of 50 really good TAs who can do what you can do with a 20 student class. So the real follow-up question was, what is it that one can do? How can you scale this in terms of the work that you give to the students that is basically processable, that has processing scalability, objective, and stuff like that? auto-grading.
So that's exactly why Mazur invented peer instruction. Mazur developed peer instruction. He thought about having, I teach at Harvard, I could have my students work in small groups. But he thought about physics courses taught around the world, and he goes, small groups isn't necessarily going to scale. So peer instruction scales. Peer instruction involves a period of time when I will lecture to the students, which we've agreed scales. And there will be a time when you say, I'm going to pose a concept question to you. I'm going to ask you to answer that concept question, and I'm going to display the results of the class on a slide. How many people got pick A, B, C, D? Multiple choice question. Then I'm going to say, okay, turn to your neighbor or turn and form a group of 3 and talk about the question and reach a consensus in your pair or in your triple. And then everybody now vote again. Generally, what will happen in that situation is through that conversation, they will converge more closely to the correct answer. If they don't, that is a signal to the instructor that, by golly, we need to be a little clearer about this. But peer instruction scales, because I can use that in any size class you want to use. So not all of them scale, but some of them scale very nicely. And that's exactly the thinking behind Mazur when he worked on peer instruction. He wanted something that would scale. Yes, sir. I'm not sure I understand the question. I'm not sure what you would mean by active assessment. At some point, I want the students to be accountable for their ability to deliver something to me and the quality with which they deliver it to me. So, is that active? Oh yeah, it's very, tests are very active. If you look at it, and if you look at a classroom not taking a test, boy, that's very active because lots of people are taking the test and the instructor is doing virtually nothing. That's active. Okay? So that would be, in a sense, I'm not sure what you mean by active assessment, but that would be active. Now, the only problem for the students is that the end result of when they complete the test is, if it's the final exam, we're over. If I learn more, that's going to be in the next course or whatever. That's not going to count for the exam. So I'm not sure what you meant by active assessment.
To hint on whether the assessment is touching upon multiple intelligence, because if it is a pen and paper test, I doubt whether it can address the multiple intelligences which exist with the individuals.
So the thing with multiple intelligence is there's a challenge there. So one of the challenges for faculty members teaching a course, and we would talk long about this tomorrow, is what are you wanting the students to learn? There are so many different things that you can pick that might be the subject of what the students could learn. There are literally hundreds of outcomes that you could pick for your students in your course. In your judgment, in my opinion, as an instructor, one of the most important things that you do as an instructor is to pick among those hundreds of learning outcomes, what are the learning outcomes that you are going to set for the course? Now, the ability of your instruction should be geared to helping students, regardless of their display of various types of multiple intelligences, because there's not just one. People have a distribution of those. Regardless of what their distribution of multiple intelligence is, you've determined in your class, these are the outcomes that I want the students to achieve. And now I'm going to go about with instructional practices best set to make the likelihood of the achievement of those learning outcomes possible for the broad set of students that I have in my class. So multiple intelligences doesn't play a role in your setting of the outcomes. Multiple intelligences could play a role in how you choose your instructional approaches. Does that help? Maybe not.
Thank you for the lecture. My question probably seemed like a counterpoint. Nevertheless, I'll probably ask it. So, what we understand by traditional teaching, if I'm correct, this has prevailed over at least a century, if not more. And if you look at the process of learning, it depends on who's delivering and who's receiving it. So, is it a kind of a conclusion of this study that the traditional method of teaching has always been subpar, has always been inefficient, but people have not realized? Or is it that there is a change in external factors today, which probably relate to socio-cultural changes, so the receptivity of the people who are now doing the same thing that was taught maybe 100 years ago has changed, and therefore there is a need or a paradigm change in the way you want to teach?
So,
I mean, this is a problem that all of us teachers face in class. We feel that people who we taught maybe 15 years ago, they were much more receptive to what we told them, and they learned as much as we wanted them to. But the current generation is not receptive because of many external factors that are beyond our control.
so you get into a challenge. So you use the term traditional approach being subpar.
Well,
that was your term. And that's always, I think, a bad way to cast it. So if you go back and you were to look in 1960, was there much research that suggested an alternative to traditional lecture would be more effective? And my answer would be no. There were some people, even as early as 1900, talking about how we should talk, how we should instruct, and so forth. But there was no real evidence for an instructional approach that offered real superior outcomes to lecture. Fast forward to 2015. We now have, hopefully the talk has conveyed that, we now have a considerable body of evidence that says alternatives to traditional lecture are available, they are effective, some of them are in fact scalable to very large classes, and that would suggest that it is time to consider an alternative to what we've been doing because we now have evidence on other approaches. So, would those approaches, if I backdated them to 1930, be more effective? My guess is the answer would be yes, but I don't have any evidence to support that. So, I think it has less to do, although it does have some to do with the changing demographics of who's going to college, it has less to do with the changing demographics, which are a factor, but more to do with our greater understanding of learning and the ways to promote learning. And now we have a greater body of research available, and my suggestion is that we should pay attention to that and figure out how to use it. So he said one more question, and I have no idea who he picked.
Sir, my question isn't exactly related to instructional methodology. I was wondering, between relative grading and absolute grading, which of these is, more accurate? And between the two, how is each affected by class size?
So, first of all, grading is inaccurate. We all should accept that. We should not try to convince ourselves that the grades that we are given, that we are passing on student performance, are somehow the perfect grade for each of those individual students. Second, as this research has clearly demonstrated, that I am better off getting students to work together to help each other to learn. That's clear from the research. Where students collaborate together, talk together, interact together, work together, you get better results in learning. However, if I'm using relative grading, then if I'm talking to these three people, and I'm saying, if you help each other out, it doesn't matter you're gonna do better, and that means that person's gonna do worse because it's all relative. Does that make sense to you? I would submit that the answer is no. This was driven home to me. Professor Richard Felder teaches or taught chemical engineering at North Carolina State University, has delivered a number of lectures and workshops, far more than I have around the world. And he was teaching this section of chemical engineering. It was a sophomore course or whatever. And he at one point saw we're in a segment and the students are having difficulty, so we're going to work a little harder on this segment. And students worked harder on the segment, and as a result, the average on the exam on that segment was 93%. Now, are you telling me that I should award the person who got a 93 a C? Because that would be relative grading. The person at the average is a C. I don't think so. I think that grading and student motivation and cooperation is best nurtured when I have a thing of saying, if you get to this point, then you will get this grade. I don't care how many other people get there. I want you, if somebody in the class gets to this point, they get an A. I don't care how many people get an A. Why are we so concerned that in a class of 100, lots of people have to get Fs? Why does this make us happy? Now, are there some students that don't do the work, that don't learn? Yes. Should they get Fs if they're poor performance? Yes. But I shouldn't predetermine it by saying I've already pictured in my mind that a certain percentage of this class has to get an F no matter what you do. I could be teaching a physics course on special relativity, and they all could win the Nobel Prize. And I could have 100 people, I have 100 Nobel Prize winners, and that would say that 15% of you still have to get an F. You know, the hyperbole is not going to come true, but the hyperbole helps make this point that relative grading, where you predetermine the percentages of grades that are going to be awarded, to me doesn't make any sense. It also inhibits student motivation. Because why would I work harder where everybody else may be working harder, where the percentages are predetermined? And also, where was it handed down? From what divine tablet was it ordained that these percentages that we use have somehow been fixed? I understand a normal curve and a normal distribution. I understand that. I also understand what it took for a student to get into the Indian Institute of Technology, Bombay. Do those people sit on the on the curve? And I'm going to say to you that none of them sit on that curve. They are all deviants. That is, they sit way far out on the course. The only people who are more deviant than they are the faculty members. This is one of the problems with faculty members designing instruction. Faculty design instruction for themselves. And who are the faculty? They are the deviants. How many people get a PhD? Small percentage. How many of those people that get a PhD go into academia? Small percentage. You who are all faculty members, deviants. Now we could say outliers, we could use a nice term, but you are not representative of the population that you're talking to. Design the instruction for the students, not for you, because you don't represent any kind of average in the students, and I would say that the students at the Indian Institute of Technology, Bombay, do not in any case represent the normal distribution that we would expect to see across the entire population of India. So I think the rationale for relative grading should be examined seriously. Thank you very much.
I'd like to thank Professor Froyd for a very thought-provoking lecture. This is a subject very dear to all of us, faculty and students. I would like to request Professor Juvekar to hand over a small memento.